talk is Sally G, speaking on p-adic Hodge theory for rigid analytic varieties.
Thanks for the introduction and thank you for giving me the opportunity to speak here. So before going to the p-adic setting, I would like to recall a result that has already been stated in this result. So when we have X, a variety over Q, which is smooth and projective, and the homology of XC over C is isomorphic to its Durham homology. The Durham homology here is, as before, it is the homology of the complex of differentials. And we would like something similar over QP. So for the moment, X will be algebraic. So here we can still use the Durham homology, but here, in fact, so when X is defined over Q, if we please change this to QP, we get what we call the p-adic homology. But this is, when we work directly over QP, this is what we will use on the topological side. And so what we want is some ring such that we have an isomorphism between this p-adic homology and the Durham homology. Tensor. So we want this for varieties over QP, algebraic, and maybe some hypothesis. And also on the p-adic homology, here we have an action of the Galois group of QP. I will call it G. And at the end, what we wanted to study the étale homology as a G representation. So we also want an action of G here. And so we have an action of G here. And we want this isomorphism to be G equivalent. Okay, so the first thing is that P cannot be CP. So CP, it's like it's the completion of an algebraic closure of QP, and it's like the p-adic version of C. And so it is different from the Archimedean space. Here we cannot have CP because, in fact, it does not contain some p-adic version. And I mean, what I mean by that is that, for example, if you consider the cyclotomic characters of G, so from to Z cross, so this is defined by the action on the P roots of the unity. So we have that the action of G is given by this cyclotomic character. G. And if I write QP1, this representation of G, in fact, QP1 comes from the Durham homology of the projective line over QP bar with QP coefficient, and we need to take the GRP of one here. And so if we want to have this, I will call it. So if we want to have this isomorphism, we need some element T in B such that G acts on T by the cyclotomic characters. So this is this element who will be like the p-adic by I. And there is a result of state that there is no such element in CP. So we need to consider bigger ring. And this is why we will use what we call the period rings of O10. So the first one is the Durham period rings. So this is a discrete evaluation ring. And we have a uniformizer T, and this T is this element 2 pi I. So we have that G acts with the cyclotomic character. So we have an action of G here, and we have that the fixed point of this section are QP. Yes, and also we have a filtration given by the power of T, and the graded pieces of this are given by the twist of CP. So you have this ring, and for this ring, we have this comparison. So this is a theorem of 5 rings. For X, smooth and proper, for QP, we have this star for B is equal to B Durham. So we take B Durham, it is the associated field. So we invert it. And so this is the first thing. And also, so we have an action of G, and you can take the fixed point for the action of G on this side and on this side. And on this side, since we have that the fixed point are just QP, we will get the Durham cohomology. So we can compute the Durham cohomology from delta 1. But we cannot go the other way with just P Durham. We cannot entirely compute the delta cohomology from the Durham cohomology using this isomorphism. We need to consider more refined period rings. So there are several of them. B crystalline inside B semi-stable inside B Durham. So B Durham, we've seen that we have an action of G. With this action, we also have it on B crystalline and B semi-stable. But on B crystalline, we also have a Frobenius. And on B semi-stable, we have a Frobenius and a monodromy operator. And using all of those structures, we can prove something better. So this is a theorem of Davidson. This is true for any, but we do not need smoothness or properness. For any algebraic variety of QP, we have this isomorphism star for B is equal to B semi-stable. In fact, this is not exactly that. Here we need to use a refined version of the Durham cohomology, of the Yodo-Kato cohomology, but this is some and in particular, so and compute the monetal, like this is the exponent. And so this time we can also using the Frobenius and the monodromy operator, we can also compute eta from the RAM. So this is for algebraic variety. I know we want to study what we call rigid analytic variety. So they are like p-adic, some p-adic version of analytic varieties. That is, we want the structure shift to be analytic functions, so convergence series. And the first case is the proper and smooth case. So in that case, so it was studied by Gilles, by Gilles and Gilles. And in that case, the homology is finite. So now we are over CP, coefficient, and this is finite dimensional over QP. And we have the same result as before, as in the algebraic case. Now for other varieties, so this is more complicated because now the data homology is not finite. So data are in fact total, but for example, for the disk, the open unit disk, or CP, the H1 in fact total, but or P1, CP, this QP coefficient is given by the O of P mod CP. So we have all the convergence series and the open unit disk. So this is big, but there are still some results.
Speak of rigid analytic in the sense of Berthollet.
Okay. And yes, so for example, for smooth Stein spaces, so Stein spaces, this means that we can cover X by affinoid UN, such that UN is inside UN plus 1, and we want the compactification of UN to be inside UN plus 1. So I will write like that. And so this means that you have this union of affinoids, and in some way you can make the structure shift over convergence. You can go a little over UN. And in that case, we have that, I mean, what will make things easier is that the current homology is concentrated in W0. And so this was studied by Gilles, Daspinescu, and Gilles. And so there is no, we do not have that kind of isomorphism, but still we can compute the Poital or étal homology from the DRAM1 and the DRAM from the Poital 1. So there are other results. So there are results for smooth quasi-compact varieties by Gilles and Gilles, and also for, quasi-compact, quasi-separated varieties by Fosco. And to finish, so my work So I am working in two directions, so extending these results by using, instead of the usual cohomology, the compactly supported cohomology. And also working on applications of these results, and maybe just an example of application. This is a joint work with Gilles and Gilles. We have proved that for X, a smooth Stein curve. So we are in the motion 1 over QP. We have a duality between the quietal homology of XQP and the compactly supported cohomology. So form quietal XQP QP2 minus J. So we have this duality result. I will stop here.
Just to clarify, in this last statement, you're writing these parentheses to mean there's two theorems. There's like a tall version.
This is quite.
It's all pro.
Yes, but I didn't want
Both
to
sides.
explain it.
What is the meaning of compactable?
So we are using a definition which is based on some papers of Gilles, and we are writing that the compactly supported cohomology XQP is given by the fiber of the quietal cohomology, the usual one, and the map to the colimit over the quasi-compact inside X. And we will
X minus U is interpreted as a
this would give.
X minus U.
This is a rigid analytics. Right. But for example, for the disk, you will remove all the closed disk inside the open union disk.
Sorry, what's the meaning of duality here? Like, are these?
There is a perfect pairing of solid. We need the solid formalism, so of solid QP vector spaces.
Do you have any expectations what happens on quasi-compact curves?
Quasi-compact, no. At the beginning, we were thinking that it would work for all partially proper curves, so quasi-compact, but now we have our strategy here will not work, but we are trying to do something more general over C. So we are trying to prove that the quietal cohomology of X QP, there is some twist. So this is the R1 in like the vector space, but with a big V and a big S, the Banach-Collins category. we are trying to prove that there's twist and shift here. And hopefully this will work for every x partially prover. But we don't know how them.
So just to clarify, we don't have any expectations if X is quasi-compact.
No, if it's quasi-compact partially prover.
Thank you.
So the term is a mixture of duality focal homology and something geometric.
Yes, so here we have a QP, and yeah, so we have some kind of coherent duality and Galois duality, and we have to do a mix of the two.
And this 4 is somehow 2 from the tape local duality and 2 from the geometric curve.